So welcome everyone to the Chem 501 seminar series and the last seminar of the fall semester. Today it's my pleasure to introduce Professor Rich Jordan of the University of Chicago. Rich is a leader in the world of catalysis and polymerizations, and obviously his research is near and dear to my heart. To give you some background, Rich got his BS degree at Rutgers, then moved to Princeton for his PhD, and did a postdoc at the University of Wisconsin-Madison. He began his independent career at Washington State in 1983, where he was promoted to associate professor, and then went to the University of Iowa, where he would eventually be promoted to full professor, and has now been at the University of Chicago since 1999. And so, without further ado, Professor Jordan, turn it over to you.
Okay, thank you.
All right, good afternoon, everyone. Let me first thank Brian for being such a wonderful host, including waiting around till 10 o'clock to pick me up at the airport last night. My flight was actually delayed by 5 hours, so I had a nice 5-hour break at O'Hare Airport, which was okay. After a couple of hours, I got all my work done, so I had 3 hours to kill, so I started fiddling around with these slides and added a few. So I have way too many slides as a result of it. So you'll see when my presentation gets a little rocky, those are the slides that I added. And hopefully we'll keep on time. So what time should we stop, by the way? Okay, great. So I'm going to tell you about a project that we've been working on actually since 1999, which is when I moved to the University of Chicago. And I'm going to tell you about one aspect of it, and it's been done by, been done by these folks here. Shuji is a former graduate student in my group. She's now at ExxonMobil working in polymers. Wei was a postdoc. He's now at Argonne working on batteries. Ernest was a graduate student, really good graduate student. He works on electronic materials now at Cabot Microelectronics. Jackie Defoe is an excellent graduate student. Now she's in law school. David just graduated. He's taken a job with a startup company in California. Gia was a postdoc, just finished. He's working for, I think it's Formosa Chemical down in Texas, making polyolefins. And Nate is a current graduate student just about to finish. And these students and whole string of other students in my group have been working to develop or discover catalysts that can copolymerize nonpolar olefins, particularly ethylene, with vinyl monomers, such as vinyl chloride, vinyl ethers, vinyl acetate, different types of acrylic monomers, and so forth, to directly make functionalized high-density polyethylene, so linear polyethylenes with functionality on the main chain. And I'll tell you about a class of catalysts that we've been working on that we and a number of other groups around the world have been working on that can do reactions like this, although very poorly, but we think it's a good lead structure, and that sometime in the next X years we'll actually have practical catalysts for this type of process. So to start off with, let me just say a few words about polyolefins, conventional polyolefins, and I know there's a lot of expertise in this department in polymers in general and in polyolefin synthesis. But I wanted to give a little bit of background to kind of set up some of the challenges that we're facing in trying to incorporate these polar monomers into these kinds of polymerizations. Okay, so the main polyolefins are linear polyethylene, so-called high-density polyethylene, different types of stereoregular polypropylene, and isotactic polypropylene is the main one, and then various copolymers made from ethylene and alpha olefins. These materials are made by catalytic insertion polymerization using, in the majority of cases in industry, heterogeneous catalysts, either Ziegler-Natta or Phillips-type catalysts, and more these days, going back the last 15 or 20 years, so-called single-site catalysts based on discrete organometallics. And of course, these are very valuable materials. We all use something like 100 pounds a year, and principally in different types of packaging and structural applications. The key to the advantageous materials properties of these very simple polymers is the polymer crystallinity. In linear polyethylene and stereoregular polypropylene, because of the regular structures, the chains will pack very nicely in highly crystalline lattices. And that gives high melting materials and good materials properties. And then in these linear low-density copolymers, you can modulate the degree of crystallinity by controlling the branch length and the amount of branching, and to some degree the distribution of the branching. It turns out that when you build in a small amount of polarity to these otherwise totally hydrocarbon, nonpolar, hydrophobic polymers, you can change many of their properties, sometimes quite dramatically. Properties like surface polarity. So if you could imagine having a few hydroxyl groups on a polyethylene chain or a few acetate groups. Those groups are quite incompatible with the totally nonpolar hydrocarbon environment in your solid polymer, so the chains will reptate to find orientations where as many of the polar groups as possible are sticking out of the surface. So it's would be a way to make quite easily functionalizable surfaces. So you could have a plastic that you could paint or print on or bond to another polar material in a laminate. Another key property for these packaging applications are the set of barrier properties. How easily small molecules and gases can diffuse through a film or through a milk jug, for example. And it turns out again that incorporation of a small amount of polarity, and apparently chlorine is really good for this, you can enhance the barrier properties quite substantially. And then a third property that we're interested in that's, I think, underappreciated is the fact that, of course, these materials are, particularly polyethylene, essentially totally non-biodegradable. You can put polyethylene in a landfill and come back in 10,000 years, it's still going to be there. You can imagine basically bugs don't like long-chain hydrocarbons. You can imagine building in a few reactive groups that will give the bugs a starting point to start some degradation chemistry. So those are the kinds of things that people are interested in, and why people would like to be able to make polymers of this type. Now you can imagine doing this by radical polymerization, and there's an enormous industry based on radical copolymerization of things like ethylene with vinyl acetate and so forth. But the radical polymerizations, first they're limited to ethylene as the nonpolar partner. And second, radical processes are normally accompanied by lots of hydrogen atom transfer reactions that compete with the chain growth steps. So you normally get highly branched materials. And those highly branched materials lack, I got to get used to this thing, three buttons is at the limit of my intelligence, I think. The highly branched polymers will lack the high crystallinity that these linear polymers have. So radical approaches aren't going to work. In industry these days, there are functionalized polymers that are made by post-polymerization functionalization, typically by different types of radical-based CH activation reactions under pretty rigorous conditions, such as under plasma discharge conditions. And this is the way, for example, that chlorinated polyethylene is made, and this is an important material actually in certain automobile engine parts. We'd like to get away from that because this is very expensive and it's very hard to control, and you can only functionalize the surface of the polymer. There are two general methods based on olefin metathesis, ADMET and ROMP, which the organometallic chemists are familiar with. Beautiful chemistry, and you can make polymers that have a variety of functional groups distributed in a very precise way down the chain. But from a practical point of view, this is not very desirable because you're starting with high-value monomers. You have to do the ROMP, and then you have to do a hydrogenation of the polyalkenomer that you get from the initial ROMP polymerization. And it's, I don't know, it's quite difficult actually to hydrogenate polymers in a clean way. So ideally, you'd like to make, for example, chlorinated high-density polyethylene by direct copolymerization. And more generally, we'd like to make, you know, a variety of functionalized polyethylenes by direct copolymerization. So that's what we're trying to do. And ultimately, you would like to have this process, you know, be a practical process that could be scaled up, although we're a long way from that. So what I want to talk about today is first, for the non-specialists, the non-polymerization people and the non-organometallics, just say a few words about how olefin polymerization catalysts work, conventional olefin polymerization catalysts, because that's going to be the starting point, and we're going to try to modify them to engender functional group tolerance to enable them to incorporate these polar monomers. Then I'll tell you about some of the specific chemical roadblocks that you run into, so ways in which the polar monomer can inhibit or poison the catalyst. And then I'll focus in on this particular class of palladium catalysts that contain phosphine sulfonate bidentate ligands that, as I alluded to earlier, I think provide a really good starting point for ultimately solving this problem. And then I'll focus in and give you a pretty detailed discussion of one particular type of copolymerization involving ethylene and vinyl ether. Vinyl ethers, as an example, will focus in on some mechanistic issues. And then I'll finish up with some work we've been doing over the last few years based on multi-nuclear catalysts that self-assemble into, I'll call them cages, as you'll see, that have some really interesting properties. Okay, so that's the plan. We'll see how far we get. So the starting point is olefin polymerization catalysts of the conventional type. And here are some examples of what people refer to as single-site catalysts. These are all discrete organometallic species. They have a metal. They have some kind of supporting or ancillary ligand. They have an alkyl group. You'll see the metals will have low coordination numbers, so you need to have one or more vacant sites, usually at least two vacant sites, where the olefin will bind. Most of the time, the metal center is cationic, so the metal center is quite electrophilic. And you can use different types of early transition metal systems and more recently late transition metals, in particular iron, nickel, and palladium. And we'll be talking about this class of catalysts today. These catalysts all work in the same way, which involves insertion chemistry. So we're going to start with a precursor. This would be a zirconocene type catalyst, which is one of the first classes of these single-site catalysts to be discovered back in the 80s. We'll start with a neutral compound, so you might call this the catalyst. We'll do some chemical step that will convert this di-X compound to the monoalkyl cation containing a weakly coordinating anion, and this is the so-called active species. The polymerization will involve coordination of the monomer to this active species to give a metal alkyl olefin species. This rearranges by what's called an insertion reaction, which is really a 1-2 shift of the alkyl group from the metal center to the one end of the ethylene to give this alkyl species, and then this is trapped by ethylene. So that's a growth cycle. And every time we go around that cycle, we are homologating the polymer chain by 1 monomer unit. Now, why does this type of reaction work, and why does it work well for something like a zirconocene cationic system? Okay, this metal is, as I said, it's electrophilic. Okay, this is a 14 electron system, so it's electron deficient, so there's a strong driving force to bind the olefin to the metal. So that's step number 1. You have to coordinate the olefin. Point number 2 is that this is zirconium in the +4 oxidation state. So it has a D0 configuration. So there's no possibility of D to pi star back bonding to the ethylene. So this line here, the ethylene coordination interaction, involves donation of the pi electron density from the ethylene to the metal center without compensation of that effect by D to pi star back bonding, which you would see in a conventional olefin complex. So as a result, in this species, the olefin is activated for nucleophilic attack, and of course you've got an alkyl group bound to the metal, so this is a polarized bond, particularly for an early transition metal. So it's delta plus on the metal, delta minus on the alkyl. So you have an activated ethylene next to a nucleophilic alkyl, and that charge separation drives the migration. If you want to push arrows, it's a nucleophilic attack of this carbanion-like alkyl ligand onto the activated olefin. We get the insertion. Now, if you just have a growth step and nothing else is happening, you have a living polymerization system, and the molecular weight will get higher and higher and higher the longer you run the reaction. But most of these insertion polymerization catalysts will have chain transfer reactions that are accessible, and these are reactions that release the polymer from the active species and then regenerate the active species. And most of the time, the major chain transfer reaction is a beta hydride elimination. This is essentially the reverse of an insertion, where the hydride migrates back to the metal. We flip these electrons in here to rearrange this alkyl to a hydride olefin species, and then there's a ligand substitution step where the monomer kicks out this polymer. So each chain will have one saturated end and one unsaturated end. Okay, so that's how these catalysts work. This mechanism is going to give us a linear polymer, and sometimes you get branch polymers. Where are we here? Particularly with late transition metal compounds, and most particularly with palladium and nickel. Okay, so this is the famous Brookhart catalyst. The active species is a diamine palladium alkyl cation. Again, there's a site where ethylene or your monomer will bind cis to the alkyl. Palladium-2 is a D8 metal, but because it's such a late transition metal, it's a very poor back bonder. So we have the same kind of electronic situation we had with an early transition metal, poor back bonding. And In this case, this is the resting state. It can insert, and then it gets trapped. If you do a beta hydride elimination, that can lead to chain transfer, as I explained before. But in these systems, the beta hydride elimination is highly reversible. So the hydride can pop back onto the alkyl. To go back here, that would be a degenerate process, or the hydride can migrate to the other end of the olefin and rearrange the primary alkyl to a secondary alkyl. And then if this binds and inserts an olefin, you get a branch. Or you can do another series of beta hydride elimination, reinsertion, to migrate the palladium one more carbon down, and then insert, and you're going to get an ethyl branch, etc. And ultimately, you get a highly branched, so-called hyperbranched polyethylene that is in fact more highly branched, much more highly branched than you get from radical polymerization. So this is called a chain walking. This process of moving the metal up and down the chain is called chain walking, and it's the other extreme of these polymerization mechanisms. So we can make linear polymers and polymers that are more or less highly branched depending on how well the chain walking competes with the growth. Okay? So that's the starting point. Now, we're interested in using these catalysts to copolymerize ethylene and other olefins with these polar monomers. And this field really got started about 15 years ago with work by Brookhart and Drent. Brookhart showed that the diamine catalysts can incorporate acrylate-type monomers, and you get, as I said, a highly branched, a hyperbranched polyethylene with sometimes up to about 10 or 15 mole percent of acrylate incorporated. And because of the chain walking mechanism, the acrylates tend to be at the ends of branches. This was a seminal advance in this field. It really, I think, established for the first time that it was conceivable that you could incorporate these monomers, which are normally polymerized by radical or anionic or cationic polymerization, into an insertion type process. But you get a branched polymer which has very poor materials properties. Then a couple years later, Drent and co-workers at Shell in the Netherlands showed that catalysts like this, based on palladium alkyls with phosphines, with this particular phosphine sulfonate ligand generated in situ, can do the same type of copolymerization, but now you get a linear polymer. And this is the kind of thing that people are interested in making. Okay, so this got things started. And people got really excited about doing this, and so tried similar reactions with many other catalysts of the type I showed you in an earlier slide, and many other polar monomers, and met with almost complete failure. In general, what happens when you try to do this with other catalysts and other monomers is that the catalyst is usually immediate. Either nothing happens, you just have a polymerization and the comonomer just sits there, or the comonomer kills the catalyst. So why is that? So again, what we'd like to do is take one of these catalysts and add in a polar monomer, and then we want the polar monomer to form a pi complex and then undergo insertion. And you'll see there are two possible regiochemistries, the so-called 1,2 insertion to put the polar group beta to the metal, or 2,1 insertion to put that polar group alpha to the metal. And then we want these functionalized alkyl metal species to be able to insert the next monomer, either the olefin or the vinyl monomer, to propagate a chain. Okay? And apparently, in these two specific cases, and a small number of very closely related systems, like using methyl vinyl ketone, for example, then that can happen. But usually something else happens, and there are 3 or 4 main problems that you run into. So these are various papers, attempts we published that met with failure, and I'll explain what we discovered. So one thing that happens quite often is that you simply see homopolymerization of the polar monomer by one of the classical mechanisms. And I won't go into this in detail, but it turns out that these metal alkyl active species are often really good initiators for radical polymerization and different types of ionic or group transfer type polymerizations of these vinyl monomers. So that's one thing that is a real problem. Second point is that the X groups typically have lone pairs, so they're Lewis bases. And the catalyst itself, as I explained, is designed to be very electrophilic at the metal center. And so the monomer can form a pi complex, but quite often the X-bound complex is favored. And sometimes the catalyst will just get stuck in this form. So if you try to incorporate acrylonitrile into polyethylene using the diimine catalyst, it won't work because the acrylonitrile just binds like this and your catalyst is dead. But as long as this is reversible, you have the chance for insertion, but then these species can form different types of chelates where the X metal interaction ties up the coordination site where the next monomer should bind. Okay, so X coordination is a big problem. An even worse problem for cases in which the X group is a potential leaving group. So vinyl halides, vinyl ethers, vinyl esters, like vinyl acetate, is that if you have an X group beta to a metal, you can do a beta X elimination and eliminate the olefin and make a metal X compound, a metal halide, a metal alkoxide, a metal acetate, for example. And this is a dead catalyst because it doesn't have an alkyl group to start the insertion. And so if you take essentially any catalyst with vinyl chloride as a comonomer, the vinyl chloride will immediately kill the catalyst by one of these beta X eliminations. Okay, so we've studied many different ways to get around beta X elimination. Only one is successful, which is what I'm going to tell you about. So then you can say, okay, to avoid this problem, let's either design or discover a system which inserts the polar monomer in the opposite sense to put the X group alpha in the alpha position. Okay? So it can't easily eliminate. The problem here is that this X group, all of the X groups of interest are inductively electron withdrawing. And so that, like if this is chloride, for example, strongly electron withdrawing, that kills the nucleophilic character of that carbon. And as I explained, the insertion is really a nucleophilic migration of the alkyl onto the olefin. We put an electron withdrawing group on your nucleophile, you kill its nucleophilicity. So normally these guys will not insert. Only very rarely will you see an insertion. And what this is going to do is chain walk, as I described. So it's going to do a beta X elimination. Either this functionalized olefin can fall off, that'll lead to chain transfer, or more generally, this will reinsert, give a species that now has the X group in the beta position, and then it does beta X eliminations. Okay? So for one of the main areas of focus of my group over the last number of years has been to figure out a way to avoid these beta X elimination processes so we can incorporate the monomers like vinyl halides, vinyl ethers, and vinyl esters. And we tried many, many different approaches, and only one has worked with any kind of generality, and that's this family of catalysts here. This is the system originally discovered by Pugh and Drent at Shell. Okay, so this is a square planar palladium-2 compound. The key is this ancillary phosphine sulfonate ligand. It's important to have a rigid backbone to this ligand to prevent the sulfonate from dissociating. And all of the successful cases so far have an arene-based linker. L is a labile ligand, typically pyridine or DMSO or THF, which will dissociate, and that's where the monomer is going to bind. And now, why did we get into this class of catalyst? As I mentioned earlier, most palladium catalysts chain walk rapidly, and that gives you the highly branched, the so-called hyperbranched polymers. But this catalyst makes an almost totally linear polyethylene. Okay, and this was discovered by Drent. And so we thought, you know, if it's making a linear polymer, that's really unusual for palladium. That suggests that for some reason this catalyst is not chain walking. Because if it chain walked, you get a highly branched polymer. So we thought, okay, if it's not chain walking, that may or may not be true. But if it doesn't chain walk, one reason for that would be that it might not do the first step in chain walking, which is the beta hydride elimination, very easily. And we thought, if that's true, then maybe it wouldn't do beta X eliminations. And so that was why we started studying this catalyst. As I mentioned, Drent studied these systems under in situ catalyst generation approaches, which really don't work very well. It's very difficult to make a clean catalyst that way. So my group and a number of others who are working in this area, and I don't have time to talk about the related chemistry that these various groups have been doing, have developed a large family of these catalysts that we can synthesize in discrete form and then study their chemistry in detail. So typically we start with what we call the zwitterion. This is the neutral form of the ligand, but the sulfonic acid, of course, is a very strong acid, so it protonates the phosphine. And these are made by starting with PCl3 or triphenylphosphite, or sometimes trimethylphosphite, and sequential additions of the appropriate aerial lithium reagents. And then you can isolate these. There are many, many examples of these that have been made now, several hundred, with different, mostly aerial groups in these positions. And a nice way to do this is then to react this with TMEDA dimethyl palladium, use the proton to protonate off a methyl group, and you generate a TMEDA adduct, which often will have this structure it's a binuclear compound with a bridging TMEDA, but there are different TMEDA structures that you can form. So generally, the TMEDA is then displaced by some other ligand, typically pyridine, to make a pyridine compound. Here's a typical structure. This is one of our favorite catalysts. So it's got the phosphine, sulfonate ligand, methyl with 2,6-lutidine as the labile ligand L. And then one of the aerials has an orthomethoxy group. The other aerial has this ortho 2,6-dimethoxy group. And I'll show you this catalyst for certain polymerizations works really well. So here's a typical crystal structure. The other thing we can do is take this base stabilized form and abstract the pyridine with a Lewis acid, and typically tris perfluorophenylborane, so-called BARF, works the best. And we can make a base-free material without a ligand here. So there's a vacant site. And then those species will typically dimerize by bridging through either this oxygen, which is most common, to make a structure like this, or sometimes you'll see it bridge through this one to make a similar structure, but with a 4-membered ring here instead of an 8-membered ring. And then we can use either of these 3 forms as, for catalysis, or we can displace the pyridine with some other ligand, and DMSO tends to work pretty well. Okay? So as I mentioned, these types of catalysts make a highly linear polyethylene. If you look closely, typically you'll see a few methyl branches, but only a few. So this particular catalyst with the 2 orthomethoxy groups in the ortho positions will give you about 1 or 2 branches per 1,000 carbons. We've done a lot of polymerization kinetics on these systems, and the results are consistent with a fairly standard mechanism for late metal catalysts, where the resting state is the olefin complex. If we start with the base-free system, that's the resting state. If we start with a ligand-stabilized catalyst precursor, we'll have an equilibrium here. And so as you jack up the ethylene pressure, the activity is going to go up, until you reach the point where the equilibrium is all the way over on the right, and then the activity will saturate. And then this will insert and be trapped, or it can undergo chain transfer. Now this insertion is pretty interesting. You'll see, note the way I've written it. The alkyl group is trans to the sulfonate, and the initial product of the insertion is this beta agostic species where the alkyl group is still trans to the sulfonate. An unusual feature of this catalyst is that the ancillary ligand is unsymmetrical, phosphine and sulfonate. Most catalysts have, like the diamine catalysts, the ligands are always symmetrical. And so there are two possible isomers for these kinds of compounds. This is the stable one, where you have this alkyl group trans to the sulfonate and the olefin trans to the phosphine. So there are two possible ways that this can go. One mode would be for this species to do a migratory insertion where the alkyl group migrates to the olefin in the conventional way to give this species, which is then trapped by the olefin, to give the unstable isomer of this, and then this can do a second insertion to go back here and then get trapped. So you would have probably a slow insertion and then a fast insertion. The other possibility is that this stable isomer isomerizes to the unstable isomer, and the unstable isomer inserts rapidly. So we have an isomerization, then a migratory insertion, and then trapping. And it seems that for many catalysts, the isomerization insertion process is the dominant process. And the current thinking is that the isomerization goes through a transition state like this, where the sulfonate isomerizes from a kappa 1 binding mode to a kappa 2 binding mode to give it intermediate like this, where you have a stretched metal phosphine interaction. This intermediate you'll see is 5 coordinate, so it's configurationally labile. And it turns out if this undergoes 2 Berry pseudo rotation events and then collapses back to the kappa 1 to the normal form, you will have isomerized it. And so this is probably what's happening in many systems. This will isomerize via these kinds of intermediates and then get trapped. But there are other systems, and I'll show you one later, where it's really hard to understand how the system could isomerize, and yet it polymerizes just fine. So it seems like the other pathway would be also accessible. So that's chain growth. And then the chain transfer is also interesting. So chain transfer is going to involve beta hydride elimination and then exchange of this olefin by ethylene to release the polymer and then regenerate the active species. These square planar compounds generally undergo, as you remember from your basic inorganic course, associative ligand substitution rather than dissociative substitution. And in a classical associative substitution mechanism, the incoming ligand comes in at one of the axial sites to give this square pyramidal intermediate. You go through a Berry pseudo rotation process that moves the outgoing ligand to the opposite axial site, and then it falls off. So this is probably how chain transfer occurs. And I'm not going to talk a lot about how you can influence activity and molecular weight by modifying the structure of this PO ligand. We can talk about that later, but it turns out that you can attain high molecular weight polymers with these catalysts through 2 approaches. One is the classic Brookhart type approach, where you design in groups on the ligand that will block the axial sites. That's great for ethylene, but when you then try to apply those catalysts to polar monomer copolymerizations, you have real trouble getting the polar monomer to coordinate because the polar monomer has a bulky X group. The other approach that we've been working on more recently is to make the system very rigid to try to slow down these very pseudo-rotation processes. And you can do that through different types of pi stacking interactions, for example. And then you can make catalysts that are not overly sterically crowded, so they can incorporate the bulky polar monomers, but still have slow chain transfer rates. Okay, so that's how these catalysts work. Now we want to think about copolymerizations, and one of the monomer classes that we've studied a lot are vinyl ethers. And we originally got into vinyl ethers because we thought these would provide a tunable class of monomers. So in addition to manipulating the structure of the catalyst, you can manipulate this R group and make it more or less electron rich or electron poor, or more or less sterically bulky. So they're interesting monomers from that point of view. And it turns out that these PO palladium catalysts, as we call them, are really good at incorporating vinyl ethers. So you make polymers that look like this. Again, they're linear polymers, a few methyl branches, and then various amounts of the vinyl ether incorporated into in-chain positions, as we call them, and chain end positions. And the chain end position is always this one with the alkoxy group 1 carbon in. Okay? This is a totally unique reaction to this class of catalysts. Okay? No other family of catalysts that I know of can incorporate vinyl ethers. Okay, you run into two problems with vinyl ethers. If it's an alkyl vinyl ether, then this double bond is really electron rich. So the monomer is very susceptible to cationic polymerization. In fact, when you buy a monomer like that, it always has sodium hydroxide or some other base in there to prevent it from undergoing cationic polymerization. And most catalysts, as I've mentioned, have metal centers that are very electrophilic, typically cationic, so they're good cationic polymerization initiators. But this catalyst has a neutral metal center, and so it's less prone to do that. So that means we can incorporate these alkoxy groups. The aerovinyl ethers have a different problem. What they normally do is a 1,2 insertion to put the aryloxy group in the beta position. But an aryloxy group is actually a pretty good leaving group. If you think about phenol, it's pretty acidic. So phenolates, not very basic compared to an alkoxy group. So it's a good leaving group. And other catalysts that we've looked at, and we've looked at many other catalysts with aerovinyl ethers, they always will do a 1,2 insertion and then a beta aryl oxide elimination. But these catalysts seem to be totally impervious to that reaction, and the aerovinyl ethers are incorporated quite nicely. Okay? So this is a unique system, and we can make lots of different polymers like this. You can influence the molecular weight and the degree of comonomer incorporation and so forth by changing the structure of the ancillary ligand. And we can get up to about 10 mole% vinyl ether incorporated. So 1 out of every 10 monomers or so could be the vinyl ether. That's the good news. The bad news is that while these vinyl ethers are competent comonomers, they also are strong inhibitors and can function as chain transfer agents. So the more vinyl ether we put into the reactor, of course, the more we get incorporated. But as we do that, the polymer yield drops drastically and the molecular weight drops drastically. So these are some numbers for T-butyl vinyl ether with this particular catalyst. When you have a small amount of T-butyl vinyl ether in there, you can get, say, 1% or so incorporated. Your Mn would be about half of this, 25,000 or 20,000. When you increase that vinyl ether incorporation level, you can see the molecular weight drops down into the oligomer range. Okay, so it works. The polar monomer is incorporated, but the polar monomer is inhibiting the catalyst and also reducing the molecular weight. So we'd like to understand we'd like to avoid these problems, and so we have to, in order to do that, we have to understand what their chemical origin is. And the way to do that will be to monitor these kinds of reactions by low temperature NMR. And let me skip this. And so for this, we use this particular ligand. The key here is that we've got these T-butyl groups in the meta position, which is going to make the catalyst very soluble. And you'll see there's no orthosubstituent here, so the catalyst will be very sterically open at the metal center, so we won't have any steric inhibition to coordination of the vinyl ether. Okay, so we can make our TMEDA complex and then convert this to the base-free dimer, which looks like this. This is a case where we dimerize through this oxygen. And I forgot to tell you earlier that most of these base-free dimers are insoluble, so they're not really useful, but this one with the T-butyl groups is very soluble. This dimer is quite labile, and if you react it with a ligand, you'll break open the dimer and form the ligand complex. So if this ligand is ethylene, and we do it at a temperature below about 10 degrees, we can see the ethylene complex. If it's a vinyl ether, we can see the vinyl ether complex. So we can look at things like competitive monomer binding. We can look at the insertion kinetics and see what else happens and understand how these polymerizations go. Okay, so for copolymerization, one of the first things you're interested in is how the two monomers compete for binding to the catalyst. And so we can just set up this equilibrium starting with that base-free dimer, measure the equilibrium constant. It turns out that this equilibrium constant at this temperature is around 20, favoring binding of the vinyl ether. Okay, even though it's bulkier, it preferentially binds over ethylene. Okay, why is that? It's because this palladium, as I mentioned, is a poor back bonder. So the olefin-metal interaction is all sigma donation, and it's the more electron-rich double bond is going to stick more strongly. And of course, T-butyl vinyl ether has a very electron-rich double bond. Okay, so we know that T-butyl vinyl ether actually binds to the catalyst more strongly than ethylene does. Then we can make the ethylene complex and warm it up, and at around 7 degrees C, this is in methylene chloride solution. This insertion will occur on the time scale of minutes, so it's convenient for monitoring by NMR. And we can measure the kinetics of insertion. We can get a rate constant. And the barrier to that insertion into the palladium methyl bond is about 21 kcals per mole. And then subsequent insertions going from the propyl to the higher alkyls are faster, and so we can't get good data for that. When we go to the T-butyl vinyl ether complex, we have to warm it up to about 70 degrees before it will insert at a rate that's convenient for kinetics. Okay, so this insertion barrier is much higher than the ethylene insertion barrier. It's about 26 kcals per mole. And the insertion goes totally in a 1,2 regiochemistry to give this chelated structure. And I'll skip a little bit here. And then this will slowly react with ethylene. We don't have a barrier for that, but we know that this is a slow process because ethylene has to displace the oxygen and open up the chelate. Okay? So what this tells us in other experiments is we have the same mechanism that I showed you for ethylene homopolymerization, but the vinyl ether can bind to the catalyst actually preferentially to ethylene. It will do a 1,2 insertion to give this chelated species, and this will slowly grow polymer, and multiple ethylene insertions will give the in-chain placement. What this species does not do is do a beta-alkoxy elimination. And if we generated this, then what would happen is the alkoxy group would deprotonate here. We'd kick out the alcohol and make a palladium allele. but we see absolutely no evidence for that. So that's a special feature of this catalyst, which enables it to be tolerant of these alkoxy groups. I talked about the binding. So as I mentioned, the vinyl ether complex is more stable than the ethylene complex. That difference is about, when we extrapolate up to polymerization temperatures, is about 1.6 kcals per mole, and the exchange between those two species is very fast. The vinyl ether complex is the favored one, but its insertion barrier is much higher than the insertion of ethylene. So most of the time we're going to go to the right. We're under Curtin Hammett conditions. And from this potential energy surface, you can work out that under polymerization conditions, the T-butyl vinyl ether binds about 10 times stronger than ethylene, but ethylene inserts about 400 times faster than the vinyl ether will insert. And that predicts, you can use that to predict the amount of incorporation that you're going to get, and it matches up quite nicely with what we see experimentally. Then the other interesting point is this N group that I mentioned. How does this form? We're not 100% sure, but we've tried to track this down using a number of approaches, and the most powerful approach is to do deuterium labeling experiments. And I won't go through those in detail. We can talk about it later, but those experiments strongly suggest that this is formed by chain transfer to vinyl ether after a vinyl ether insertion. So we picture that as this chelate being opened up by T-butyl vinyl ether, which is, again, a much stronger ligand than ethylene, to give a species like this. If this inserted, we would see two vinyl ethers in a row in the polymer, which we have never seen. We know where those shifts would come in the NMR. We've looked, we've made model compounds like that. We have not seen it. So this doesn't happen. But the other thing this can do is chain transfer, and it's probably by a direct chain transfer to monomers. So a direct migration of hydrogen from here to here to kick out this product and generate this intermediate that has the alkoxy group in the alpha position. And then this will grow, ultimately giving this N group. That's what we think is happening. And so this process is an extra chain transfer process that leads to reduction in molecular weight. And these two intermediates, this chelate, which is kind of a resting state because the ethylene has an extra step it has to go through to break open that chelate to grow. And so it's not very reactive. And this guy's not very reactive because of the electron withdrawing effect of this alkoxy group that I talked about. The formation of these intermediates, we believe, is the key source of the inhibition to the polymerization that we see from this polar monomer. Okay? So that's a little bit about that's a little bit about vinyl ethers, alkyl and aryl vinyl ethers. This catalyst will also incorporate vinyl fluoride, which kills other catalysts primarily through beta fluoride elimination. We'll incorporate vinyl acetate, which is pretty amazing because this will kill other catalysts by beta acetate elimination, which is a really fast process. And as you can see here, can incorporate a wide variety of other monomers. So it's quite a unique system. One of the key features, we think, particularly for these monomers that are susceptible to the beta X elimination, is the asymmetry associated with this ligand, and particularly what we call the electronic asymmetry, the positioning of a strong donor, phosphine, and an exceedingly weak donor, a sulfonate, cis to each other. Okay, it's a very unusual ligand in that sense. Now, why is that important? It's important for the following reason. This is palladium-2. If you think about your hard, soft, acid-base theory, palladium-2 is one of the classic soft metal ions. It's like mercury-2. So in systems like that, trans effects are very important. The metal-ligand bonds are highly covalent. It's a very polarizable system, and the ligand here strongly feels the ligand trans to it. And the stable isomers will always have a strong ligand trans to a weak ligand. Phosphine trans to pyridine, alkyl group trans to sulfonate. Strong bias for that geometry. So when we're doing, where are we here? Ethylene homopolymerization, as I mentioned, the initial product from an ethylene insertion is this agostic alkyl, and we've characterized some of these by low temperature NMR. From the point of view of trans effects, this guy's, happy as a clam because you have the phosphine trans to the agostic interaction, which is really weak. You have the alkyl group trans to the sulfonate, strong trans to weak. So electronically, it's perfect. If you do a conventional beta hydride elimination, which would lead to chain walking and chain transfer, you lose that optimum positioning of strong and weak field ligands because the phosphine ends up trans to a hydride, which is bad, and you've converted this alkyl group to a much weaker ligand. So this is not as favorable as this. So there's an electronic bias against the beta hydride elimination. It can still occur, but it's disfavored relative to other catalysts. And so the ethylene trapping outcompetes it, and we go to growth, and we have a tendency to form a linear polymer. And the same effect operates. This is our story, and we're sticking to it. It's our working hypothesis. The same effect we think operates with these vinyl monomers. So you insert, as I showed you, you form these datively stabilized chelates. It's great. Strong trans to a dative interaction, which is very weak. Very strong trans to very weak. If it does a beta X elimination, which a symmetrical catalyst is likely to do, you get to a species like this, where again, you've lost this very strong trans to very weak arrangement as we have converted the alkyl to an olefin, and this is less favorable than this. So again, there's a bias against that process, the trapping, which leads to incorporation of the polar monomer rather than catalyst deactivation, outcompetes it. So we think the real key to these, there are a number of important features, but this electronic asymmetry we think is really important. Now, in the last few minutes, I want to show you one other system. I've extolled the virtues of these PO catalysts, and the main virtue is that they have unique tolerance of these functional groups and a unique ability to incorporate these polar monomers. But you notice I haven't really said anything about activities or molecular weights or anything in detail about how much of the polar monomer is incorporated. And the fact of the matter is that as catalysts go, these are really terrible catalysts. They're not very active. You have to do a lot of ligand tailoring to get high molecular weights, and you'd like to have MNs of, say, 200,000 or higher to get good materials properties. That's very challenging. And as I've mentioned, when we go to the copolymerizations, then those problems are exacerbated because the polar monomer will be an inhibitor, and the polar monomer can turn on additional chain transfer pathways. So to move this area forward, we need to drastically, we need like a quantum leap in quantum improvement in the overall performance of these catalysts. And through really interesting system, as you'll see, we think we have an interesting way to get around the problem of molecular weight. And it's based on ligands like this, which we call OPO ligands. It's just a phosphine with two of the aryl sulfonate arms. I won't go through why we started studying these. It was for a totally different reason. But we can make these ligands, and when you put them on palladium by substituting chloride and cod from this precursor, you form compounds like this where this OPO ligand binds in a bidentate fashion to give a square planar complex with one of the sulfonates not coordinated to palladium. This is a chloride derivative, so it's overall anionic. We can displace chloride with methanol, And then you have a dynamic system where the free sulfonate can exchange with the bound sulfonate, can displace methanol with pyridine. You can pull off chloride with silver to make a base-free species, and then you can react that with pyridine, and you can make other derivatives. We've made a bunch of other analogs with different ligands here, and we've made about 5 or 6 of these OPO ligands with different substituents off these aryl groups. And then you can look at their polymerization behavior, and it turns out that they do something really interesting. So a conventional PO catalyst exhibits normal single site behavior. So we have, as I mentioned, we've got growth by insertion, chain transfer by beta hydride elimination. You get Schultz-Flory molecular weight distribution characterized by a poly dispersity of 2. And here are 2 examples where you've got either ethyl groups here or methoxy groups here. So this is what a conventional mononuclear catalyst will do. These OPO systems really surprise us. They give bimodal molecular weight distributions with a low molecular weight fraction with this particular ligand of around 10,000, and then a high molecular weight fraction with a molecular weight of around 1 million. The overall polymer is totally linear. Tm is about 136 degrees. And so this is a late metal catalyst that's making a totally linear polymer with this very high molecular weight. So what's going on? Well, if you've got a bimodal molecular weight distribution, and we were talking about this, I guess, earlier with somebody, generally it means with the students, yeah. It generally suggests that you're forming 2 active species. So with these precursors, something's happening in solution. We're forming 2 compounds. One makes the low molecular weight, one makes the high molecular weight. We're interested in finding out which of those, what is the structure of the species that's making this high molecular weight fraction. Because if we knew that, we will have solved one of the key limitations of this whole class of catalysts, which is the inability to make high molecular weight polymer. Okay, so in order to address that, the first thing we needed to know was what the structure of our starting material was. We knew by NMR that the PO ligand, this OPO ligand was binding in a bidentate fashion, but we really didn't know what this, we called it the dangling sulfonate. We had no idea what this was doing. And, lithium really wants to be 4 coordinate, and there's no way you can get 4 coordinate lithium with 1 sulfonate group. So there's something interesting happening structurally. And it took a long time for us to figure out how to crystallize these materials, and the key was this particular ligand. We call it PY prime. We call it David's ligand. David was a graduate student who figured this out. It's a beautiful ligand because this branched alkyl, of course, is going to make your compounds very soluble, but the arms are long enough so that when you look in the crystal structures, you start to see those alkyl chains pack on top of each other, just like the same structure you see in solid polyethylene, so they crystallize well. So we could take this base-free material, add in this pyridine prime, and crystallize it, and we get out a material that is a tetramer in which 4 of these units are held together by an internal cage formed from this lithium sulfonate here and 1 of these oxygens. We call those the assembly elements. This is the structure of, we've got a bunch of these structures now. This is the first one we made. So let's start here. Here's the palladium. Here's the phosphine. Arene. Here's the chelating sulfonate. 1 of the oxygens is terminal, 1 bound to palladium, the other is bound to this lithium, which is part of this cage. The so-called dangling sulfonate is over here. Sulfur, oxygen, lithium, sulfur, oxygen, to second lithium, sulfur, oxygen, to a third lithium. So through this type of interaction, 4 of these guys come together and form this cage. So there's a pyridine here, here's a palladium methyl, Here's another palladium, and there are two on the bottom rotated 90 degrees. The overall symmetry is S4. My favorite point group. Any synthetic chemist always wants to make at least once in their career an S4 symmetric compound, and this is S4. So the phosphorus is at stereogenic center, and the sulfur is a stereogenic center. So this is S and R, and the one over here is S and R, and these two on the bottom have the opposite configuration. If you go through the various diastereomers that you can form, it turns out you can form 6 different diastereomers. We've made them all on the computer, and they all look perfectly fine, but we only ever see this one for reasons that we don't understand. Okay? That's what we have in the solid state. But in polymerization, this thing is going to go in solution, and so we really wanted to know what the solution structure was. And we were able to figure this out by NMR. So this is the NMR spectrum in tetrachloroethane at room temperature. This is the palladium methyl signal. You see it's very clean. All 4 of those palladium centers are equivalent by symmetry, by the way. So we see 1 palladium methyl group, 1 phosphorus signal. The palladium methyl is shifted to very high field, around minus 0.4 delta, whereas a normal palladium methyl in these compounds comes at around plus 0.5 delta. So this palladium methyl is about 1 ppm upfield. If you look at this structure, the methyl group on one palladium sits right under the pyridine ring on the neighboring palladium. This is a top view. So this is a methyl group. This is the pyridine on the other palladium. So you see it's in the shielding region. And so this high field shift was immediate and very strong evidence that this cage was being held together, was holding together in solution at room temperature. And we can also study this by pulse gradient spin echo NMR, which shows it's a tetramer, and by electrospray mass spec, which shows it's a tetramer. When we warm it up, though, you'll see this new species coming in. Here's a palladium methyl in the normal region, and you see a new P31 signal coming in. This is an equilibrium process. If we cool this down, it'll come back to here. Pulse gradient spin echo NMR shows that this is a monomer, and we can do this as a function of concentration and fit the results to different equilibrium expressions, and this fits very well equilibrium involving dissociation of the tetramer into 4 monomers. So in solution, this cage falls apart to 4 monomers. And then we can correlate the molecular weight distributions that we see. And you remember, I showed you sometimes, depending on exactly how we do this, we can get more or less of this high molecular weight fraction. So we can correlate what we see in the GPC with the speciation of the catalyst, which we can determine by NMR at the initial stage of the polymerization. And whenever we have a lot of this to start with, we get a lot of the high molecular weight polymer. Very good correlation. So it doesn't prove anything, but it's, we think, very good evidence that it's the cage that is making the high molecular weight fraction. Now, why would that be? I talked about chain transfer earlier and the importance of this associative chain transfer mechanism and the importance of being able to access the axial coordination sites in order to do chain transfer. You'll see in this cage, the cage totally blocks one of the axial sites on each palladium. So that could be one reason. Second reason is that this cage is pretty rigid, and so that could also inhibit very pseudo-rotation processes that you have to go through to do chain transfer. And a third possibility is the following. If you look down on the top, these are the 2 palladiums. This is the methyl group, and this is the pyridine. This is the nitrogen of the pyridine. So this is where ethylene binds. So this catalyst, if it grows multiple chains off each cage, so if we're growing chain off this palladium and this palladium at the same time, the two chains are growing into the same region of space. So there's going to be a lot of steric interaction between the two growing chains, and what my current thinking on this is that because of that, the mobility of the chains is restricted, and that may prevent them from bending over to get to the conformation that they need to get to undergo beta hydride transfer. So that's, hand waving, but at this point, but that's what our thinking is. So now we're trying to skip this. We're interested in the problem we have with that first generation cage is, as I've shown you, they fall apart very easily. So it's really tough to study them rigorously. So we're looking at some other cages based, instead of lithium sulfonate, on things like cores like aluminum phosphonate or zinc phosphonate cores that we know from work in the main group chemistry area are going to be much more robust than the lithium sulfonate cages. Okay, so with that, I'm going to stop. I'm sorry I ran a little bit over. And again, I mentioned that the key people who helped us, who did this work, and one guy I want to mention is our crystallographer, Alex Filatov. If you're doing organometallics and inorganic chemistry, particularly with these large structures that end up giving you all sorts of problems with disorder and funny space groups and the rest of it, you really need good crystallography support. And so he's a key member of our team. So thanks again for a great day, and I'd be happy to answer any questions.
So I have a couple. The vinyl ether, when it binds to the palladium-7, unless ethylene comes along, it's totally dead end. Because you said at one point, and that was a question I had, you never get two vinyl ethers to polymerize together. Correct.
So if once you do a vinyl ether insertion, if you've got
Then ethylene.
you do a vinyl ether insertion, then either ethylene can bind, that will be a productive step, or vinyl ether can bind. The vinyl ether can't, at that point, you can't do an insertion. So you've got two possibilities. It's going to fall off and ethylene will go on, you'll continue to grow. Or you do a chain transfer, which generates a hydride vinyl ether species, which then inserts apparently 2,1 and then grows to give that N group that I showed you. That was the idea. And everything fits that. The one piece of, I don't want to belabor the point, but the one problem we have with that, so we haven't published it yet, is that we've never found, So if this binds ethylene, great. If it binds vinyl ether, this is stuck, so it can go back, or it can do this chain transfer. This should produce this type of side product, which we never see. And we think this is now really susceptible to cationic processes, and we think it's getting chewed up. So we have a few more control experiments to do with that.
Polymerize two vinyl ethers together.
I think that it's primarily a steric issue. This is pretty crowded. It's almost like a tertiary carbon. So that's going to slow it down. And remember, the barrier for this insertion with just a simple primary alkyl without substituents in the beta carbon is already pretty high. It's 26 kcals per mole, so that's pretty slow. With the diimine catalysts, the Brookhart type cationic, they're a lot more reactive. They're like 1,000 times more reactive than these guys. And a number of years ago, with certain vinyl ethers, so try aryl silovinyl ethers. It's a sweet spot in terms of the vinyl ether structure where you don't see cationic polymerization and you don't see beta siloxy elimination. And in that case, we showed you can actually insert up to 3 in a row in a stereo specific way. It was really cool, but that's the only case. Yeah.
PO ligand. One of the, yeah, there we go, that one's fine. A lot of these look sort of like a tosylate group, you know. But one of my questions is, have you ever looked at the electronics and changing the backbone on that ring? You know, with like electron withdrawing groups, try and make the sulfonate an even weaker donor to increase your electron exchange between the olefin and the sulfonate on the other side. So like, obviously changing the electronics on the phosphine is well understood, but the sulfonate might have an effect as well by having a more electron withdrawing ring in there. Have you looked at anything like that? Like on nitro?
No, we're in the process of doing that now. So what so what is known is that if you make the phosphine a better donor, if sterics aside, if sterics are relatively constant, better donor phosphine works better. The growth rates are faster, the molecular weights are higher. If you change this to like an ethylene linker, it's too floppy, and the catalysts aren't stable, so the sulfonate problem comes off. We were thinking along your lines, so the first thing we do just was add to something like this, add a second equivalent of Lewis acid, and it binds here to make a zwitterine with a plus charge on palladium, and this is now a really weak donor. Those are really active for dimerization of ethylene to butene. Phenomenally active, but the chain transfers really fast. And so no one has really looked much at changing the electronics here. So we're in the process of doing that now, but we're actually first starting with making it more electron rich. So we've got a catalyst, it's got a methoxy here, it's got a methoxy here and here, and then the other one has 3, and I can't remember if they're here or here. We've made several of them, we haven't done any testing. Yeah, we'd like to do that. So nitro or CF3 would be a good one. Yeah, yeah. We made some CF3 substituted aerial ones, and they were terrible catalysts.
Other questions? So I'll ask one question. Sorry, the cage structure is kind of, it's hard to wrap your mind around how you go from 10,000 to a million molecular weight, right? And express that. Earlier on, you were talking about how the sulfonate, it kind of does this ligand walking, if you will. And you're kind of talking about the rigidity of these clusters. Do you think that might be inhibited? Can it still walk the sulfonate in these types of clusters?
I don't think so. That's, let's get a cage here. Yeah, so
the business about whether the catalyst just works in the normal way where you insert one way and then it inserts another. The barriers will be different because you're starting with different isomers versus isomerization. There's no experimental evidence that pertains to that. That's all from DFT. We have studied, that's all from DFT, but we know they can isomerize, and we had a couple of cases where we could generate at low temperature a mixture of the favorite isomer and the unfavored isomer in a model system, and we could study the isomerization. Kinetics, solvent effects, structure activity correlations, and everything fit with this mechanism where the sulfonate goes from a kappa 1 to a kappa 2. So I'm pretty sure that can happen. But this cage really you can't do that, right? Because you'd have to break this sulfur, this oxygen lithium interaction. And what we see in the equilibrium we've done the equilibrium studies for 4 different cages, and they're all perfectly tetramer to 4 monomers. So once you break, once you pull one of them off, then the whole thing falls apart. So I just don't see that happening for this system. However, truth in advertising, you heard the way I phrased what I said. We haven't really proven that this cage is so what we need to do is, we have to have a cage. This is what we're excited to do, get a cage that holds together, and we can study by NMR, and we can, like activate one corner of the cage, see what it does, activate 2 palladium centers, see what they do, really do a serious study. But it's just not feasible to do it until we get a cage that holds together. So that's kind of step 1. Okay.
There's a minor question on it, but I wasn't going to bore everyone with. Did you ever look at